Thank you for taking the time today to have a look at AC Tech's Newton Discrete Element Modeling software. Specifically, we are going to discuss Newton Chute. Please note that we have over 10 hours of full video tutorials on using our Newton software available on the web. As such, we're not going to get into specific details on necessarily how to use every feature of the software, but rather a quick overview of what Newton Chute is, how it differs from Newton Basic and Newton Professional, and how you can use Newton Chute to improve your transfer chute designs. AC Tech's Newton DEM software was originally developed back in 2004 as a multi-purpose DEM program. There's a huge range of engineering problems and equipment which can be modeled using Newton Professional. However, over the past few years, we've really found a lot of users who specifically want to use DEM for transfer chute design. And although there are some fantastic features in Newton Professional, these users just wanted a very easy to use, but yet very powerful, accurate, flexible DEM software package to just do transfer chute design and to do it at a very competitive price. AC Tech is a world leader in overland conveyor design. Our Sidewinder conveyor design software is used by hundreds and hundreds of individuals and companies around the world. As such, we felt providing these users with a very cost-competitive, easy-to-use transfer chute software package would be an absolute ideal solution and a win-win scenario for everyone. Certainly, there are many DEM packages on the market. However, to get the required features needed to correctly model a chute, most of these software packages have been very expensive. And as such, historically, DEM modeling has mainly been used on large-scale projects or by very special users or consultants. However, we now hope to bring the benefits of DEM modeling to everyone involved in the chute design process. Back in 1998, I presented a paper that at that time was one of the first DEM papers for modeling transfer chutes. And I'd like to quickly show a slide from it again, as I feel it's still very relevant today. That's why use DEM. The correct modeling of granular flow using DEM method has the potential to be one of the most significant scientific advancements in the mining industry today. Previously, general rules of thumb and past experience were the only tools available to the design engineer. And that's what DEM is. It is another tool that we have in the toolbox. It doesn't replace good engineering experience and knowledge. It's not going to replace our 2D and 3D software. It doesn't make our sticky material magically free-flowing. It doesn't negate the requirement of doing lab testing and having a basic understanding of the materials you're working with. But when it is properly used, it gives the designer a fantastic insight into the material flow and behavior inside a transfer chute. There really is no other way that we can get such a great feel for the flowability of the chutes, how making small changes to this or that can affect the design of the chute, being able to compare two different designs to one another and see what affects or doesn't affect various aspects of the flow in different ways. Looking at abrasion wear on the chutes or impact wear, minimizing that wear, minimizing material breakage and dust in the transfer chutes. Those sorts of aspects that we can now quantitatively get a good feel for. This can significantly help to improve the design, mitigate the risks that are commonly associated with transfer chute designs. But it's only if the modeling is done correctly. And this is the area where we hope you find Newton Chute absolutely excels at. So with that, let's go ahead and get started. So we'll go ahead and launch Newton and create a new file. And essentially, once we go into Newton, we've got four main options here. This is our general input window where we specify the file name, where we're going to save the files, the simulation time, various input properties of the software. We then have our geometry, which this is going to create our incoming feed and our receiving belts, as well as our chute layer. We've got our material properties and our generation the generation of the material. So these are really the 4 windows we're going to work with. Again, full set of tutorials that you can take a look at all the details. But let's go ahead and start. So with pretty much any of the versions of the software, you're always going to use a third-party CAD package, and that may be Inventor, maybe Solid Edge, SolidWorks, whatever you really choose. I'm going to just go ahead and open a simple AutoCAD DWG file that just has a very, very basic geometry in it. So there's our geometry. I'm going to go ahead and save that as a DXF file and overwrite that. And when I go in here, I can go ahead and import CAD. Now again, we support STEP, IGES, IGS, STL. Those are much more common formats. I'm not a super 3D CAD guy, so I'm pretty simple here. But going to go ahead and open that file, and there's all our different layers, and we can bring that all in. Now the one thing we won't bring in is our receiving belt, because in Newton Chute, the feeding and receiving belt we create right in the software itself. Those are the layers that are going to have movement, and we can give them their movement properties. So I'll go ahead and import everything else, and by default, again, you can see we've already got a feeding belt that defaulted to 1,000 millimeters. We're actually going to make that 1,200, and a bunch of different properties with that. Actually, I'm going to look at a side view of this here. Let's go to this side view right here, and if the conveyor was inclined, I could incline it. I can specify whether it's rotated. The head pulley diameter I actually happen to know is 600, I believe. And I can go ahead and set up all the different properties of this belt. If the pulley had an elevation, if it was an elevated head pulley, say 125 millimeters, I can just enter that right here. I can put, if I know my transition length, say a 3-meter transition or a 2-meter transition, I can go ahead and specify that right here. So it automatically puts in this transition length and pulley offset, which is really important for transfer chutes, that you include that if you've got an elevated pulley, because that's going to slightly change your belt trajectory. So it's things like that that we've tried to make really easy for the end user. And this belt happens to be going 4.5 meters per second. So that's really all we're going to specify for the incoming belt. Now a receiving belt, by default, it just puts a receiving belt in line. I'll click on this, and it drops it 3 meters below and gives it a little bit of an offset is all. Again, 0, 0, 0 is the center of our pulley. That's just what we've defaulted to. You can in your AutoCAD files, you should put all your components with the head pulley at 0, 0, 0. If you don't, you can go ahead, when you import it, you can adjust that offset, but it's just a nice reference point. So with our receiving belt, looking from a top view, we can see that's got to be rotated 90 degrees. So we go ahead and just put in 90. So that's now just rotated the belt 90 degrees. All right. That also has a speed of 4.5 meters per second. And now we can see we need to put it in the right position. So let's just start with the vertical position. And I'll go back to AutoCAD here and just say, all right, what is that offset? Well, from the center of my pulley, that happens to be 1.94 meters. So I just put in minus 1.94 meters and puts the belt right there. From a plan view, if I look from a top view, I say what's the offset from the center of my belt to my 0, 0. It happens to be is at 1.31 meters. So I come back over here and I put in 1.31 meters. All right. Now from a top view, looks great. And we may want to make this belt just a little bit longer. I'll make it maybe 6 meters, and we can see that now we need to shift it because we're actually going in the minus X direction. Again, right hand rule. So we will just shift it maybe 5 meters back. So that's just starting that starting point. And there we go. So it's pretty simple. Incoming belt we don't have to do much with. We can put in our incline angle and whatnot, put in our belt width. Oh, our receiving belt also is 1,200 millimeters. Let's go ahead and put that in. And really the only trick of this is you import your head chute at 0, 0, 0, or like I say, when you imported, you could typed in that offset. And then the one thing you do usually have to get from the AutoCAD drawing is just where is that receiving belt. Maybe it was rotated not at 90 degrees, maybe it was 45 degrees or 30 degrees or whatever. But that's just a matter of entering that receiving belt. So that is really it. The only other thing we may want to specify, we don't have to, is say we wanted to get the impact on the receiving belt. We wanted to say, okay, how much impact is this going to do on the receiving belt? I could go ahead and subdivide that right here. So for each triangle in my input, I can say save triangle force and work data. I'm just going to say yes. And in my geometry, it's now going to save the impact and abrasion work on every triangle in the simulation. Obviously, I want probably a little bit better resolution here, so we've already specified nice things that you can just put in, say 50 millimeters. Now just subdivided the belt up for me in little 50 millimeter triangles, which is excellent. If I wanted to get it on the head chute, I could just go over to the chute, into my hood, I guess, not the outside. I want this hood, this yellow colored one, and I can equalize it right here. What equalize does is it just takes these long triangles or these long squares, and if I equalize it, there, just tried to square everything up nicely for me. And then if I want to subdivide those, I can just hit divide triangles, or I can hit it again, or I can hit it again. Maybe if I want them a little smaller, I can put in, maybe I want them 45 millimeters, or I can hit them again, and there we go. Just a few clicks, we've taken our shape and meshed it all up nicely. We're going to record our data on our receiving belt, and we're done. Specified our incoming feeding belt and our receiving belt, and that's it. Now when it gets into the material generator, again, we've tried to make this very, very easy for people to use. You can go ahead and customize all your individual particle shape. There are hundreds of particles in here, or a whole slew of different particle shapes that you can go ahead and use in Newton. You can create your own particle sets, whatever you want, but we've made it very easy. We've actually put all these particle sets in here for you. Typically for a material handling chute, you might use a 40 to 100 millimeter set. Or if you got something smaller, maybe a 30 to 60 or 25 to 50. And just to show you what the difference of those looks like, I will start with just spheres, which is horrible. Don't run simulations with spheres. They're great for just running a quick simulation and saying, okay, do I have my geometry? Is everything set up right? In fact, if I go ahead and just say run right now, we've got to add the particles. So we've got spheres. Let's say this is coal. We'll say 800 tons per hour, or a density of 800 kilograms per meter cubed, and let's put in a tonnage of 1,000. So that's all we specified. We specified a particle set, a density, and a tonnage. If I go ahead and generate this, that generated a whopping 8,000 clusters and 8,000 particles, because they're simply spheres, so a cluster is a particle. And I could go ahead and say run. Just going to minimize that. And there we go. We are running the simulation, and there's nothing wrong to do this. I mean, this is running real time. Maybe we want to just check and look at this output file to make sure all the data is recording and whatnot. This simulation is probably going to take us about 5 minutes to run. And it's nice. So we can see, yep, our material is flowing. We've sometimes you might have forgot to put a velocity on the receiving belt, or did something silly or goofy with your geometry. So using spheres for that is just fine. I'm going to go ahead and just stop this and go back into my geometry. But when you get to running the real simulation, you want to use a real particle set. So for example, if I chose 40 to 100 and I generated these particles, it's going to create all our particles that we're going to use in our simulation and tell us some information. There we go. So using a 40 to 100 millimeter set, we've generated 38,000 clusters, or 135,000 particles. And again, this is limited in Newton Chute to 350,000. So we just used about 1/10 of the particles that we have available to us. And there's nothing wrong with going ahead and running this simulation. And there we go. Particles are dropping. But of course, since we've got more particles, it's just going to take a little bit longer for the simulation to run. I'm going to go ahead and stop that. realistically, let's go ahead and if we go to 30 to 60 millimeter particles. Now you got to remember, the smaller you go, the size goes up as the radius cubed. So it's not like you cut the size in half and you get twice as many particles. No, if you cut it in half, you're going to get 9 times as many. So when we went to 40 to 60, now we're up to 123,000 clusters, or 300,000 particles. So roughly a third of our capability. And you can see this is starting to look, really quite nice, a very fine particle set. If I went to a 25 to 50 and I generated that, we would end up with, and we're creating the particle sets, about 243,000 clusters. So again, this is all well within the limits of Newton Chute. 243, still well under 350,000 limit, and this is getting to be a very, very fine, very nice looking simulation. Quite frankly, the 40 to 60 was probably just fine for this transfer chute. So again, we can go ahead and just start running the simulation, and I've actually already run these, so I will open up those data files. I'm going to just minimize this. Go over and open up a new version of Newton. So you can have on the same PC with Newton Chute, you can have as many of Newton pre and post processing windows open as you like. I can still have one solving in the background. You can only have one solving at a time, though. That's the limitation. And I'm going to go ahead and open a playback file. So as a reference, I actually ran a few different cases. I ran the 30 to 60, the 25 to 50 particle set on one of our more powerful PCs, which happens to be a dual 8-core. So there's 16 cores on that. So again, this had 600 and almost 50,000 spheres, 240,000 clusters, and that actually took just over 4 hours, 4 hours and 10 minutes to run this full simulation. So still very, very quick. And you can see this flow looks very, very representative. We're still only at 7 seconds here. Now, conversely, you may say, well, that was one of your fast computers. I ran this on one of the slowest PCs that we had. I ran just the 30 to 60 millimeter set, which, if you remember, was about 125,000 clusters and about 335,000 spheres. So this is the 30 to 60, and you can see it still looks excellent. It's a very, very similar flow to the 25 to 50. And just looking at this and say, look, this 30 to 60 is almost every bit as good as the 20 to 50 or 25 to 50 set, but it had half as many particles. And this ran on just an i5 4-core PC, and it took just over 4 hours, about 4 hours and 15 minutes. Likewise, I wanted something in between, and I just did a screenshot here of my notebook computer. So this I got about 2 months ago. This is an i7 4-core machine again. It's 4-core with hyper-threading, so there's 8 functional cores. And this took about 3 hours, just over 3 hours to run. And this I had got at Best Buy for just under $1,000 US. So you don't need a super fancy supercomputer to run these at all. General i7 notebook, i5 notebook nowadays will run these simulations just fine for transfer chutes. And in this type of timing, you can run 3 or 4 simulations overnight on a regular PC for a transfer chute. So I'll go ahead and just visualize that again. Again, this was the 30 to 60 set. And there's our flow. Now, if you remember, we had also recorded impact wear. So let's go ahead and just say, all right, let's see what is the impact wear on the belt. I'm just going to zoom in so I can see the bottom of the belt. I'm going to go over here for belt number 2 and show us the work data. So I can go ahead and just play this. This is again the output result file. And what we're looking at is the impact belt wear on the belt. And if I go over to the Work tab here, I can look at impact or I can look at abrasion. This is quite handy here. So if I stop this, clearly if we start the simulation, until material starts hitting the belt, we don't have any impact. And then once it hits, we have some impact. And what this is doing is this is taking a moving average. So generally, if you're looking at design A and design B, and you've got two different designs and you want to compare the two, what you can do is you can come over here and say, all right, it takes, let's say it takes 5 seconds or even 10 seconds, whatever it takes for you. On this shoot, it's probably easy steady state by 5 seconds, but we'll just say start at 10 seconds and go to 15 seconds. And what this will do is it starts the simulation at 10 seconds, so we're at a nice steady flow, and until 15 seconds, so for over 5 seconds, it's just taking the moving average over those, over all the impact on the receiving belt. And now why this is nice is now I can take and change and look at a different shoot option or a different design option, and I can compare that with the same particle set, same particle properties, and say, all right, with shoot design A, this was my impact, and maybe I'll normalize that on 1 for a maximum, or let's even say 0.7 or 0.6. You can see the more sensitive we get, the more impact that's shown there. We're just setting that resolution, say 0.75. And I could look at that, and like I say, now I could run design B and compare that. And we've done that in some of the demo examples if you go ahead and look at them. Likewise, if I take a look at the hood, we had subdivided that. So I'll turn the belt off. If we had looked at the hood and looked at the work on the hood surface, same type of thing. And you can see, if you remember, when we subdivided this, the chute that we brought in was the actual liner plates here. So it had these discrete changes in the profile. But then we took those liners and we subdivided those into smaller and smaller squares. And that's why we're seeing these distinct impacts right where the liner slope is changing, which is what you see if you have real lives. Obviously, if we had a perfectly smooth curve in there, we'd have to put in, or we could just bring that geometry in as a curve and finally mesh it. But in this case, we had these individual plates at these discrete slopes. So I think that wraps it up for this. The last thing I want to discuss that we haven't is material properties. So I'm going to go ahead and close that. So I'd like to start out by just showing this simple video, which is a simulation with the exact same geometry, same number of particles, same shapes and sizes. The only variance is the internal material properties. So as would be expected, we can get a huge range of material flow, everything from very free-flowing to a small amount of cohesion, to more medium cohesion and sticky material, to extremely cohesive material. This is another area that we think the industry has sort of, at least the software industry has sort of left the end users hanging. We specialize in material handling, and therefore we have our own material handling lab. We do a lot of this testing in-house, and therefore we've got a very good feel for it. However, we're also working with partnerships with some of the other material testing labs and individuals around the world, so that you can get material testing done wherever you'd like to get it done at. And we want to work with you on getting the material to match the simulations to match your real-world material. But just to show you some of the basic testing that's done is everything from just looking at angle of repose and measuring the angle of material repose. Again, we work mostly with bulk solids, so we're working with the coals, the phosphates, the iron ores, various materials that a lot of our users are working with in our SignRunner software. You can look at that and tilt it at various angles and simulate the same thing and try to get the material to start sloughing off, all the way to some simple small scale. This is a very small scale flowability test, just with some soybeans in it. You can do the same type of tests a little bit larger with coal in it. This is some fines. This is phosphite fines, actually. You can, obviously things like playground sand is one of the more difficult actual materials to handle, because you can see it can build straight up like that. And of course, you can do other things, look at various exit angles. These are, again, some standard materials that we work with, and look at modeling those. Here's another whole range of different materials in full-size flow testers, from limestone to P-rock to coal again. And I mean, obviously at the end of the day, the point of that is to be able to put those those properties in, and then get the identical material properties. And this flowability test is just one of the tests that we do. Here's another one with the same thing, looking at different simulations, and again, keeping everything the same and just changing the material behavior. And then once you've done that, you can say, all right, this one best matches the real world and the real world results. That would finish. But there's also a range of drum testing. We found this test, and there's a range of different material tests that we do, but this one is actually quite nice too, because this gives you some steady state results for a dynamic test. That happens to be coal. This is an animal feed product that you can see has got some interesting behavior. Wood chips, iron ore. And again, taking that and putting that back into the simulation and getting the simulation to match. Here's our wet playground sand again, sloughing off, and the simulation matching that up, which is really quite nice and quite powerful. So if we go back into Newton and we look at our input material properties, going back to the file that we were working with, essentially we've got all of our inputs, and we've tried to make this as simple and as intuitive for users as we can. There's things like coefficient of friction, and you can specify these properties for material to material or the material to the surface. In fact, we could go into each individual layer back on the geometry page and specify properties for individual surfaces. So obviously if we've got ceramic liners in one section and steel liners in another or whatnot, we can actually specify those individually layer by layer, or here we can just specify them globally. We also have two effects here. One's called the Ratchet Effect, and the other is the Liquid Bridge. And again, there's a lot more that we can discuss on this, but in a general sense, our ratchet effect is a function of our normal force. So material that impacts and compresses together, it takes now a force to pull those particles apart. Whereas our liquid bridge is more of a viscosity type effect, like a honey, if you would, that you can put a force on it, but it applies this, or it makes this viscous molasses type flowability. And we found that these two effects really can allow us to model a whole range of material behaviors. Now, certainly nothing beats material testing. There's no question about it, and having testing done on your material is the best solution. A lot of users will look at this and go, geez, I just really have no clue. And therefore what we've actually put here for various kind of default materials, if you will, and this actually scales with bulk density, which is also a very powerful feature that's just all done behind the scenes. But it's a nice slider bar that represents material properties. So for example, coal, which again in the real world it never has a specific properties. There's some materials that are very homogeneous and uniform, but most of the stuff that we've got to work with bulk solids engineers varies from summer to winter, or various parts of the mine, or different weather conditions, and so on and so forth, that we have a range that we need to look at. So we very well may look at coal, for example, and run a simulation at the first notch, which actually is this flow right here that I was talking, or we were discussing just a minute ago. And if we look at that flow from a front view, and we zoom in here and just play that, This was actually ran at the first notch, so there was just a small amount of cohesion on there, and we can see that's flowing fairly well. It's not the greatest chute because we do have kind of a stagnation zone there, but it's flowing very well. If we then move this up to, say, the third notch and run a simulation, which I just happened to do for you guys here, which is right here. I just ran a few seconds of this, so I could go ahead and compare that. Oops. This up here. So this is now going from that first notch up to the third notch. We can now start seeing this stagnation zone increasing and the material starting to build up. But really, for this on the third notch, that's actually flowing very, very good. Once you get up to the fifth and sixth notch, that's really getting to cohesive material. So for like a typical coal transfer chute, this is probably a pretty worst case condition, and it's still flowing very well. And again, if we had any issues with our geometry, they just jump right out at you when you start running these higher cohesion cases. So this is an excellent example of the type of results that and the things that you'd be able to look at with the software. The last feature of the software that I want to discuss is essentially the post-processing of the software. Newton Chute comes with the full suite of post-processing tools that is available in the professional version. Just to quickly show you some of that, I mean, you can color particles by all sorts of things, by uniform color, by their specific cluster type. You can make them transparent or color certain groups a different color. If I wanted to color all of group 6 red or some other color, I could go ahead and do that. Clearly by velocity, which is what we've been using today. You could add a velocity tracers with that, so we can always this is a useful view of tracing the velocity positions, and you can change properties of the tracers and whatnot. We can color by a fixed Z position. Again, if I fix that Z position, you can see it essentially just colors all of the particles by their current Z position and then tracks those through the flow. So there's really just a whole different range of visualization parameters that we can work with. Certainly, if we go back to our particle shapes, we can actually mesh our shapes. So you see here, all of our clusters become these nice, smooth, mesh type shapes, and there's again a number of tutorials discussing how you work with the mesh shaped particles. I think you will quickly find with DEM simulations, using strictly spheres is a problem because spheres will not, you can't get the even simple angles of repose with spheres. So you end up doing things like fixing the rotation and things like that are physically impossible. But once you start using clusters, whether you use cluster type A or B or C or a shape with 8 clusters or irregular, long, irregular shapes, I mean, it's important to have the general shape of the particle correct. However, in DEM, a lot more impact is going to have on what you use for the material properties themselves. As we were just talking a minute ago about testing and the different types of testing to be able to get those adhesion cohesions effects are going to have a huge impact on your simulation, at least much more important than the actual shape of the particles themselves. I mean, certainly we need to have a proper size represented shape, size distribution of the particles, but those input parameters are far more important. But by all means, you can run these nice smooth shaped or visualize these nice smooth shape clusters. In the animation or the AVI creator, again, the full suite of tools. If I go back here and I just reset my simulation, say I want to look at some view here, I can add keyframes. This is simple to do. I can run the flow through here, add another free keyframe. Maybe I'll rotate and zoom in here. Let's add another keyframe. Perhaps at this point I will turn on vector traces and run vector traces for a little bit of the flow. And I can go ahead and make up my whatever animation that I want with using keyframes. Again, there's full video tutorials on this. I can click AVI. I will select my codec, which just looks at all the available video compression codecs that you have installed. The XVID is quite popular, and it will go ahead and create my animation here. And there we rotated, changed to the vector flow, and we'll make up this nice little animation once it's done. Now this is an AVI file that we can then send our client. Likewise, we can go ahead and we can save single playback frames, which is just one snapshot in time with the full 3D files. These are very, very small files. You can then freely distribute the Newton viewer to any of your clients and send them that one playback file, and then they can rotate and look at the shoot themselves. So using Newton, you can make up some really fantastic animations. This one just shows a double rock box system with a lower curved chute in it, and you can see how we just started the animation as a solid chute and then went to a transparent view, and we're just showing the material as a function of its velocity. In a second here, the receiving belt is going to stop, which it just did, and the feeding belt is continuing to run or decelerate. And there again, as discussed earlier, we can put a deceleration time for both belts and then put a restart time in as well. So in a second here, the receiving belt is going to go ahead and restart and pull out the material. But you can see this is quite nice to be able to look at some worst case conditions, make sure that we've got enough volume in the chute, have a feel for how the chute's going to pull the material out of that chute when the conveyor goes and restarts. Those are the types of things that we can look at. This next video is simply a splitter where the material comes up into an upper rock box and splits off between two pant legs. Another type of example, this is a 180-degree transfer chute. So again, doing this by just drawing this out and laying this out is quite difficult, but with DEM you can really get a good feel and visualize how that flow is gonna flow through the transfer chute. Another type of double rock box design. This is a nice animation just showing another double rock box with a lower curved spoon at the lower section of it. Again, you can see the particles are clusters that have been meshed, which makes a very nice looking final animation for your clients. This next video is simply this was actually a cold transfer with a curved chute on it. Clearly this is the medium to high friction case, and even under that, the medium friction case here, it's plugging up. So obviously that would be an area that we look at and say, okay, what do we need to do to change that design to keep that from building up? In this example here, this was just a quick little example of bin that was feeding a feeder. We cut across cut a cross-sectional view of it, so now we're looking at the middle of the feeder and just kind of how the material is going to pull out inside that feeder, and where we're going to get higher wear areas and stagnation zones. And here's just another, actually this was brought in from a STL file. I believe this was in Inventor that this was drawn in. But there again, just direct impact dropping down onto a receiving belt, and with a nice meshed particle set colored by cluster type and velocities. So that just gives you a bit of a idea of the various things we can do with the animations. So I hope I've provided a nice overview of the software. By all means, please visit actech.com for more information, or you can go to demsoftware.net and to our pricing page, which gives the various features of each of the different versions, capabilities of each, as well as online pricing. If you have any questions whatsoever, please feel free to contact either our Idaho or Minnesota office, where we'd be happy to discuss the software with you.